Hi guys, welcome to the Generative AI Hub. Today we're going to be talking a bit about how we can generate text embeddings using the decoder component of a large language model. So to learn more about this topic, we're going to be diving a bit deeper into a groundbreaking paper which has come out of Microsoft called Improving Text Embeddings with Large Language Models. So I'll admit prior to reading this paper, I was under the assumption that the encoder component of the transformer architecture is what is used to generate embeddings. I didn't really know how we could use the decoder component to generate embeddings. And that's the reason why I found this paper very fascinating. So let's unpack this concept together and learn a bit more about how we can generate text embeddings using the decoder of an LLM. Let's now talk a bit more about the contributions of this paper. This paper basically explores how you can generate text embeddings using a decoder only large language model. Their claim is that they can generate very high quality text embeddings using synthetic data generated by large language models and then fine tuning a decoder only LLM on the synthetic data. This entire training process takes less training steps compared to the training process for an encoder text embedding model. This approach also allows us to leverage the power of extensively pre-trained large language models. This approach achieves state of the art on text embedding benchmarks like MTEB. Before we dive into the technical details of this paper, I thought it could be helpful if we get a refresher on some of the key concepts behind this paper. Let's start with contrastive learning. Contrastive learning is a fundamental technique to generate text embeddings. The concept behind it is very simple yet powerful. The idea is to feed the model both similar and dissimilar documents so it learns how to distinguish and relate them. By contrasting documents, the model can better understand the underlying semantics and learn what makes documents similar or different. Now, let's talk a bit more about some of the loss functions which can be used with contrastive learning. One such very popular loss function is InfoNCE or information noise contrastive estimation. The fundamental idea here is that you want to contrast a positive example with several negative examples so that you can encourage the model to distinguish between them. So over here, basically have a query, you have a positive keys, and you have a set of negative keys. The idea here is that you want to penalize the model for having a high similarity for the query and the negative keys. And you would want the similarity between the query and the positive key to be as high as possible. This is a very popular loss function and it's used in many embedding models, the training for many embedding models like SimCLR and CLIP. Now let's talk a bit more about the different ways in which we can generate text embeddings. One of the very popular ways for generating text embeddings is using sentence birth, where we first pre-train sentence birth and then fine-tune it to generate task-specific embeddings. Now, sentence BERT basically extends the BERT architecture to generate fixed size sentence embeddings. Sentence BERT uses pre-trained BERT model as its backbone, and it adds an additional pooling layer to convert the token embeddings for the entire sequence or sentence into a single vector representation for the sentence. SentenceBird is trained using a contrastive learning objective. The aim is to make embeddings of semantically similar sentences closer in the vector space and dissimilar sentences further apart in the vector space. Now, as we discussed earlier, to perform contrastive learning, we need two things. We first need data that constitutes similar and dissimilar pairs, and we then need a way for the model to define and optimize similarity. So, for the second part, we've already discussed the different loss functions which can be used for contrastive learning. But let's talk a bit more about how we generate the data for contrastive learning. A very popular way to generate pre-training data for SentenceBird is to use natural language inference datasets. Natural language inference, or NLI, basically refers to a task of investigating whether, for a given premise, a hypothesis entails it, contradicts it, or is neutral. So, in this manner, using an NLI dataset, we can generate negative examples and positive examples, which can be used for contrastive learning. Now, let's talk a bit more about the pre training process for SentenceBird. In the pre training process, we basically use a Siamese architecture as visualized in the image. As we can see, we have two identical BERT models which share the same weights and neural architecture. These models are fed the sentences from which the token embeddings are generated. We then run these token embeddings to a pooling layer to generate individual sentence embeddings. Once we have the individual sentence embeddings, we can use loss functions like InfoNCE or softmax loss to identify if similar sentences are close or further apart in the vector space. Another approach to generate embeddings is using unsupervised techniques. To create an embedding model, we typically need label data. However, not all real world data sets come with a nice set of labels that we can use. We instead look for techniques to train the models without any predetermined labels, which is basically unsupervised learning. So, one such approach is transformer based sequential denoising autoencoder. This approach basically introduces noise to the input sentence. So, we basically mask out certain words of the input sentence, pass it to an encoder, ask the encoder to generate the token level embeddings, which we then pool to generate a sentence level embedding. This sentence level embedding is then passed to a decoder, and this decoder basically reconstructs or generates the original sentence. And the idea is that if the sentence embedding is as accurate as possible, then the reconstruction will be as close as possible to the original sentence. So, this is another approach for generating embeddings. Now, we've talked about how we can use SentenceBird to generate embeddings. But coming to the training paradigm for SentenceBird or for any other encoder model to generate text embeddings, it's mainly a two-stage approach. In the first stage, you pre-train these models on billions of weakly supervised text pairs. And then in the second stage, you fine-tune on high-quality label datasets. So in the second stage, you're basically fine-tuning on task-specific or domain-specific datasets so that you get more relevant text embeddings. The drawback of this approach is that a lot of manual effort is required to curate these datasets. Also, these datasets are constrained by the diversity of task and language. So the question which arises is, why not move from encoder only LLMs to generate embeddings to a decoder only LLM? These decoder only LLMs, for example GPT or Mistral, have a lot of pre training, which leads to very good language understanding. This means that you basically don't need a two-stage training approach to generate the embeddings. You can suffice with only a fine-tuning step on a high-quality dataset to generate the embeddings, which means that the amount of effort to generate the dataset also reduces because you only need a high-quality dataset now. There are also many other benefits of these decoder-only LLMs. Some of them are multilingual and they have a long context window. All of these can be used to generate more useful and high quality text embeddings. So, we've established why decoder only LLMs can be useful in generating embeddings. So, now let's dive a bit deeper into how we can use these decoder only LLMs to generate embeddings. So, in the paper, this is the approach they use to generate embeddings, sentence embeddings. Given a pre-trained LLM, we append an EOS token to the end of the document and feed them into the LLM to obtain the document embeddings by taking the last layer EOS vector. So this might be a lot to unpack. So I guess it might be useful to better understand how the decoder LLM works and how we can use it to generate embeddings. Right. So let's start by better understanding how the generation works for a decoder only LLM. So to begin with, we might have an input prompt, for example, once upon a time. Now this sentence once upon a time is tokenized into token IDs. These token IDs are then converted into embeddings using an embedding lookup. We then pass these embeddings into a stack of transformer blocks. So these embeddings now go through multiple layers of self attention, feed forward, and normalization. Now, the output from the stack of transformer blocks are basically going to be embeddings which have better understanding of the surrounding context. So initially we had static embeddings, and now after the stack of transformer blocks, we have more dynamic embeddings which have better understanding of the surrounding context. We then pass these embeddings into a language modeling head, which converts it into a set of logits for every token in the vocabulary. We then pass it through a softmax layer to convert the logits into probabilities for each token in the vocabulary. After that, we might use some sort of strategy to pick the next token or next word. You can use different strategies. For example, we might use a greedy strategy where we pick the token with the highest probability. Now this process is repeated until we hit the end of sequence token. So this is basically the process or the generation process for a decoder only LLM. So now we have a decent understanding of how the generation works for a decoder only LLM. And by generation, we mean how do we predict the next token given an input prompt. So now this decoder only LLM generation process can be kind of broken down into three steps. The first step is generating the static embeddings. The second step is passing these static embeddings into several transformer blocks to generate more dynamic embeddings, and then passing these dynamic embeddings to a language modeling head to predict what the next token would be. Now, if we leave the last step, which is the language modeling head, and only look at the first two steps and look at how the dimensions look for the input, you initially begin with a sequence of length capital T, where T is the number of tokens in that sequence. You generate the static embeddings for each of these tokens, where the size of each embedding is small d. So after generating the static embeddings, you have an output of shape t comma d. You then pass it into the transformer blocks where you have self-attention, feed-forward, residual connection, and layer normalization layers. And the output here is going to be of shape t comma d. Now this is how the output looks before you pass it into the language modeling head. To generate embeddings using a decoder-only LLM, we do not need the language modeling head. We use the output from the transformer blocks. So what we would do is basically take these dynamic embeddings generated by the transformer blocks, and in particular take the embedding for the EOS token and use that as the embedding for the entire sequence. So to summarize it, suppose you have a document to be embedded. What you do is you take the document, append a EOS token to that document, pass it through the LLM, and after the transformer blocks, you would have a set of dynamic embeddings generated, and you would take the embedding for the EOS token and use that as the embedding for the entire sequence. So this is how you would use a decoder only LLM to generate embeddings. So now let's dive into the method or approach they use to fine tune the decoder only LLMs to generate embeddings. So to begin with, let's talk about how they generate synthetic data. To basically use an LLM to generate the synthetic data, they use a two-step prompting strategy where they first generate a list of task definitions and then they generate query document pairs for each of the tasks. So in this manner, they're able to generate diverse synthetic data and high quality synthetic data. So the idea behind this two-step prompting strategy is that first you generate a list of task definitions and then you categorize these tasks into different categories, and for each category you would use a different prompt to generate the synthetic data. So in this manner you have higher quality and more diverse data. So the task categories are basically asymmetric tasks and symmetric tasks. By asymmetric tasks, what we mean is that the query and document are semantically related, but they're not paraphrases of each other. So within asymmetric tasks, you can have multiple subgroups, for example, short long short, and long long. Basically, short long, what that means is that you have a short query and a long document. Long short, you have a long query and a short document, and so on. And then you have symmetric tasks where the query and document are semantically similar but differ in surface form. So these are basically the task categories and the approach in which they generate the synthetic data, which we can use to fine tune the LLM on. Now, within the paper, what they say is that the best results they achieved for the embeddings was when they used a mixture of synthetic data and data from existing data sets. Now let's talk a bit more about the training process or the fine-tuning process of this decoder-only LLM. Now, as we mentioned before, you can either use the synthetic data set or a mixture of the synthetic data and data from an existing data set, like MS Marco. So what they do is that they take the original query and they add the task definition to the original query. And in this manner, you get an augmented query. So that's the first step. You augment the query with the task definition. The second step is generating the embeddings of the query and the document. You basically append an EOS token to the query and the document. You pass it through the pre-trained LLM and then you take the embedding of the EOS token as the embedding for the entire sequence. So that's the second step of the process, generating the embeddings for the query and the document. Now let's talk about the training objective, which is basically the info NC loss, which we talked about earlier. The model is trained using info NC loss, and the goal is to maximize the similarity between the query and the relevant document while minimizing the similarity with the negatives. And the way we measure similarity is using cosine similarity with temperature. So this is the overall training process which they use to fine tune the decoder only large language model. Coming to the results, when fine tuning Mistral 7B on only synthetic data, they found that they achieved competitive performances with the two-step training paradigm of encoder-only models on benchmarks like BEAR and MTEB. But when they fine-tuned on a mixture of synthetic and label data, which they have taken from existing data sets, they achieved new state-of-the-art results with around 2% improvement, which is a significant improvement. The key insight here is that generative language modeling and text embeddings share a deep understanding of natural language. So let's break this down a bit more. These decoder only large language models like Mistral 7B have been exhaustively pre trained. What this means is that due to this pre training process, they have a good understanding of natural language. And this good understanding of natural language is critical for the way they are able to generate text, and is also critical for the way they are able to generate text embeddings. The key point to note here is that generation or generative language modeling and text embeddings both require a good understanding of natural language. And hence, we can leverage these decoder only large language models which have been exhaustively pre trained. So, in conclusion, this paper first talks about how you can use LLMs to generate synthetic data sets to fine tune your text embedding models on. Then they talk about how you can use decoder only large language models like the Mistral model and fine tune on the synthetic data sets to achieve competitive performances on the text embedding benchmarks. They also claim that the training process is much more streamlined and efficient than the existing multi stage training approaches. This is mainly because they're leveraging the pre training or exhaustive pre training of these decoder only large language models, eliminating the need for a multi stage training paradigm. Finally, we'll talk a bit about the limitations or the scope for future work, which they have listed in this paper. One limitation is the increased inference cost. LLMs like Mistral 7B have higher inference costs compared to BERT style encoders. There also is higher storage cost when it comes to these decoder only large language models. Synthetic data generation in this approach requires a lot of manual prompt engineering for high quality outputs. So there's still some amount of human effort required to generate high quality synthetic data. So a scope for future improvement here could be automatic prompt optimization for better synthetic data generation.